Okay, so this seems to be a common thing here. I thought after the pandemic, like somehow sanity started to reign. Wrong. It must stop. It really must stop. It really, I don't know if I can work too much longer. I'm gonna have words.
Yesterday they were testing the, I think it's a beat, and this is like going off all day, it's constant beeping.
Yeah, I don't know. I mean, isn't it like torture enough? Like, isn't that torture enough for so many students? Like, do we have to do this to like? So I was up very late last night grading top 3 exams, and then this morning my coffee pot broke, which is like maybe the worst thing that's happened to me all year. So I'm sorry ahead of time for all things. All right, so last time we ended with sort of a very nice result, which distinguished 2 different notions of sort of primeness, one we called prime, reducing. So this proposition, 2 notions, same so long as the ring we're in is a PID. If R is a yield domain, and prime, if and only if the prime will always imply irreducibility, but irreducibility is not primeness in general. Prime, remember, this means that P divides AB. There B. Divisible means P equals AB. AB is unique. Two. And what I think, at least for me, when I was learning this, even still today, oftentimes throws me off a little is that when you learn it initially, this is the definition. Okay, so what we're going for is we wanted to show this one kind of like inclusion in our Venn diagram that was maybe not, well, hadn't been proven yet. If I have a principal ideal domain, then I have this fundamental theorem of algebra. I can uniquely factorize things to irreducibles. This proposition will go a long way into showing us. I mean, it's almost easy after this proposition to show the uniqueness part of that. I showed the. So I'm just going to state that theorem. I did also, by the way, do like I cut off sections 4 and 5 for this week. Before the class, I left 3 on there, but I might just like go over some of that today. I'm not sure. So I won't grade those. Okay, so here's our theorem. For this view, we're going to have to establish a few limits. Here, add the existence of factorization. Why not irreducible factorization? All right. As I said last time, Noether had this really beautiful theory that is still an active area of research of theory meanings. And the baby version of our theory is what we'll use. So, number 1, every A R any 0 or unit. It has an irreducible effect. This is for a PA. That's kind of, let me assume that R is a PID. So first, because A is not 0 or a unit, it's either irreducible. If it's irreducible, okay, so if not, let's say if A irreducible, if not, then factorization. A equaling, say A1. What is the definition of irreducible? It says that if our A is irreducible, if every factorization, well, A is not equal to iterative. If every factorization of A, either one of them or the other is a unit. So if it's not irreducible, there's some factorization where both of them are not units. So so then there is some factorization A where A is equal to A1 times B, where both are not units. That means that A1 properly divides it. So we can say that A is contained, principal ideal generated by A is contained in the principal ideal generated by A1, but that they're not equal. If they were equal, B would have to be a unit. Okay. So make the same argument with A1. If A1 is irreducible, and we just found an irreducible factor of A, and we're done. We're after some irreducible factor. So if A1 is irreducible, we're done. If not, we can factor A1, just like we did with A. Get another inclusion, say A2. Keep on going, right? We'll continue inductively. What we'll get is this ascending chain. Now the question is, what happens if we have an ascending chain like this, where we have strict inclusions each time? In other words, we don't have any altogether. Something goes wrong. Let's suppose this chain is indefinite. If it stops, then we're at an irreducible. Got that. Here's the trick, which is really cool. Take the union of everything. I equaling 1, 2. What do we say about this union? You can say two things. You can say that if we have two elements in this union, well, then they're going to be two, there's going to have one element, say here, maybe one element up here, right? But this is contained in this. This ideal is contained in this. So you have two elements somewhere up here. If there are two elements up there, you can add them together because they're principal ideals. So they're closed abelian groups. In other words, this thing is going to be an abelian group. Similarly, if I have any element in here, it's going to be in one of these guys. If I take that element and I multiply it by another part, it's still in there because this is an ideal. So that means that this is closed under multiplying by elements of R. Those are the two properties that define an ideal. So this whole thing is an ideal. But now, being an ideal and being in R We know that this is a principal ideal domain. That means that I must be generated by some guy, some single element. AB. Like our AB. Call it C. So what?
So C is irreducible.
Well, I don't know. I would see it to be reducible. I'm sure it violates, I mean, maybe it is. Maybe there's an argument there. But that's not what I'm looking for. What's wrong? I'm under this assumption. C is in this.
Oh,
thing.
C is the end of the chain.
Right. C is in this thing. C, and that means that C is in one of these. It's the union of an infinite number of things, but C is a single element. To be in a union, you have to be in one of the sets that you're taking the union. So C is in one of these AIs. So the C is in a capital N, some big N. Big. That implies that AN, well, the principal ideal generated by C is contained in AN. Yeah.
What is the N?
Capital N?
Yeah, and then like.
Oh, this means like sufficiently large. Like just take it as big as you need to. It's just saying, I mean, it could be, N could be one. Like, I don't know, it could be whatever. But it's just saying, like, there's some big enough N. So if this is, but this is contained in C, because this is contained in R. Maybe you can say it this way, every other plus one. Now you're saying that a set is strictly contained in itself. Properly contained in itself. It's equals, there's an equality here. So that means this must be equal. So this must stop at some point. And that says that when it stops, you cannot further factor. You cannot further factor into irreducibles. So that thing that you had factored in. Okay, so now we know that if we have an element of our ring, we have an irreducible factor. Now what we want to do is prove kind of a variant of what we just did and say that given an element of any element of our ring, not a unit or zero, that we have a finite factor. Not two, but sort of the same trick. I love it if one of you smart guys or ladies could come up with like a proof that does this all at once. Like this is the same argument, but I can't get my head around doing it at once. How it feels. Well, I don't know. And I see in most texts they do it separately. There's got to be like a slip way. So every A has finite organization. Now, it's definitely true. There are rings where you don't have, where you have elements that don't have an irreducible factor that are not units. It's also true that when you do have such a thing, where they're not finite. So this is all hinging on, right? Which is this is something. The proof is it though is the same kind of argument. What we do now is we use lemma 1. So by lemma 1, A has an irreducible factor. We write it, and now we'll write it as A1 times B. Actually write it. B1. If A1 is irreducible, done. Right, we've got a finite irreducible factorization. Otherwise, we find factorization. A1 is equal to A2. Now we continuing. Get A is equal to B1, B2, B3, dot, 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 up to Bn times An, where An may or may not be irreducible. So the question is, does this terminate? But again, this kind of factorization is equivalent to an ascending chain. A contained in A1. Here we have strict inclusion, proper inclusion. Like this. And so long as A sub n is not irreducible, we can continue. Find the irreducible factor and proper. But we know based on what we just did that this must end. This game must end. Let's get to a point where by the previous argument. Must be. And which is a bad irreducible. That's equivalent to being able to not find. Once you're at that point, then all right, questions? All right, so now we want to finish the proof of the theorem. Now we have that every element has a factorization. I want to show that this factorization is unique. Up to reordering of the factors and taking associates. You can always do those two things. That's got that. Let's call this like 3. A is equal to P1 PR equal to Q1 S P R two factorizations P I and Q J are reducible. Then number of factors is the same, R equals S. And reordering we can assume that PI, QI has principal ideals. Say they're associates. I star is equal to that. Well, to prove this, you sort of prove this by maybe induction on the maximum of R and S or something. If it's one, then they're both irreducibles. You have a single equality. And here I'm sorry, I should have, well, base case is silly. Base case just be clear. And now let's assume, so it's assumed true. And S, say S or R, but let's say S or R. To prove an induction. All right, so we have P1, PR is equal to, what do we do? If it's an induction proof, you want, like any induction proof, what you want to do is you want to take your n+1 case, reduce down to. How could we take this S, which is n+1, down to a statement about something?
I don't think we're allowed to divide, but you could divide by QS.
You're not allowed to do anything, right? You're not allowed to, but you want to do that, right? That's what you want to do. You could do that if you knew that one of those QIs were like one of the P's. If you do that, you have cancellation. You're in a domain. So cancel out. So let's see if we can just say that one, let's say P1. This is, okay, there's, R has to be greater than or equal to 1. It can't be 0. This can't be a unit. This is not a unit. None of these are units. Not 0. So I'll assume that and work out the details of that. So the P1, the claims that P1, P1 divides. This is obvious. P1 divides P1. All these guys, right? I mean, all you have to do to see that is associativity. P1 times something equals that. P1 is irreducible. Turn on PID, P1 is prime. Dimensions are the same. P1 divides a product of things. What does it mean to be prime? It says if P1 divides a product of two things, it divides one of them. That's for two things. But you can kind of use a recursion. So okay, P1 divides this, which is equal to Q1, Q2 through QS. But since P1 is prime, it divides Q1 or it divides this. If it doesn't divide Q1, it divides this, then use your recursion. So okay, P1 divides Q2 times Q3 does. So then it divides Q2 or it divides the remaining ones. Keep on going, and at some point, it's going to divide one of these. Let's. Yes. Recursion is like the opposite induction. Go down. Recursively include P1 divides J. Some J. This is because reducible. Definitely using that thing that we worked hard to show. Okay, so P1 divides QJ. What?
QJ is irreducible.
QJ is irreducible, so what? Close. P1 divides QJ. J equals P1 something. Something. Means definition of irreducibility. That A is a unit. They may not be equal. They may not be equal. They're still it's right. Visible. And PI is not, or P1 is not a unit. So, that means that we can, well, what we can do is we can do the following thing. So, P1 times P2 PR plus Q1 to Q2 minus 1 times QJ, which is P1 times A. Again, friends. Take plus 1. QS. And now we do have Now we do have cancellation. Cancellation. We can absorb this unit into any of the other irreducibles. Multiply your irreducible unit, still an irreducible. So then we get this equality, P2 R Q1. I told it, let's say we absorb Q1, it's still irreducible. And then we omit, this is notation for omitting the J guy. Hat on it. That's it. Now we've achieved our induction step. We've reduced down to, now the maximum is one less. We have uniqueness. We have that this S minus 1 is equal to R minus 1. S must equal R. And we have that all of these are associates of each other. But QJ and P1 were associates of each other. So that gives us the uniqueness of that. More or less clear? Less than more. Good enough. Great stuff. Okay. Now that we have this, what do we do with it? So now we have what we want to do is a unique factorization is very useful. Very useful. So what we'd like to do is study a little bit about factoring polynomials, and we're going to get more like basic in a sense. Not be so abstract in that we're just dealing with some general ring R. We're going to focus a little bit on the ring of polynomials with coefficients and integers, and ring of polynomials with coefficients and irrationals. These are very like complicated actually. I mean, the rational one not so much, but actually, yeah, the rational ones. So yeah, these are very. I mean, number theorists would say, you know, like these are the things. Well, many of them would say these are primary things of interest. So, I don't know if you like numbers. We have a few of them here. So, yeah. So many. There's early. I like them. All right. Yeah. What? Nothing. I don't have a beef with them. I mean, compared to like, I mean, I have a beef with analysts. I mean, I like them all here. I'm friendly with everybody. But you know, the subject. How do you mean analyst? You know. I mean, okay, I get it for some like side areas. I have a beef with those guys. Number theorists, so they do beautiful. I have a beef with the number of number theorists. You know, there should be less of them. And that's not because it's just like proportionally, like the open and interesting problems. Like, that's subjective. You know, the interesting problems in math. I don't know how many are number theory problems. I mean, there are people like Terrence Dow who are like awesome. That guy's a wizard. All right, so what we want to head to, which I don't think we're going to be able to do today, is sort of this next section, which is factorization. Sort of understand the relationship between factorizations and polynomials with integer coefficients. Those are rational coefficients. Even if you're not interested in numbers per se, but you're just interested in like working in the real world or the complex world, there's a lot you get out of understanding this, like, and understanding this. That is a very complicated. All of the sort of like number extensions of our usual arithmetic, given by trying to find solutions to polynomials. So in some sense, that ring governs a lot of interesting things. But I did want to give you guys, because I don't think you'll ever get it again unless you continue math. Happens. But not intentionally. But just give you a picture of a fundamental theorem of algebra. I can't prove for you, but I can kind of explain. Because this one is one, I mean, very important theorem, and it's a very nice theorem. And there are many proofs, and all of the actual like rigorous proofs rely on some kind of pretty advanced math. Like first year grade. There's a picture. There's a picture. You can't understand. So what does it say? This theorem says a function, polynomial, complex coefficients, and it's non-constant. So, not true for reals, right? Not true at all for reals. That's all. A lot of polynomials and reals don't. But for complex numbers, you always have. So let's see if we can explain why it's. So for this, I need to kind of talk a little bit about what complex arithmetic looks like. I know how many, some of you know it, have an idea, but some of you don't. Learn. But it's beautiful. It's really wonderful. So this is like all kind of what does minus. So addition in complex numbers, you all know, right? So I have an A plus BI. Add them. You just add them like you're adding vectors. Make a parallelogram. Add them together. A plus B, right? Plus C plus B. Addition in the complex plane, which looks like vector addition. Nothing special. What does it mean? What does multiplication look like? I'll say I have a Z. What is multiplying some random element? So the question is this question. What is multiplying? This is what, maybe this looks completely like gibberish. In other words, what I want to do, so, okay, so what is adding? Adding looks like translation. Right? If I add an arbitrary thing to a plus bi, what does it do? I can think of a plus bi as an action on the entire plane. And it just translates it up. Right? This guy gets translated up that much. This guy will get translated up that much. I add a plus bi to everything on the plane, I'm translating the entire plane. Okay. I'm asking the same question now about multiplication. What does multiplying by a plus bi do to the entire complex plane? Okay, raise your hand if you know. Are you thinking? You might. To feel very tempted. This hand raise. You're not too confident. I'm going to call on Caleb.
Doesn't it rotate it?
Okay, doesn't it rotate? Yeah. What do you think?
So it rotates it by b radians, and then it either stretches by the magnitude or it stretches by.
Close and close. Almost and almost. So you guys all know your polar coordinates, right? It's like Cartesian coordinates, A, B. Make isomorphisms. There's also polar coordinates, theta and r. You can represent, do you know how to represent a complex number? Who knows how to represent a complex number in terms of theta and r? Beautifully. I'm seeing two more hands. Right. Yeah, you don't have your hands. There's another one. And it's algebraic, analytic. D, this is B is equal to E R. That's a real number. E I theta. Get your head right. It's true too. I'm not even lying. In the sense that there is like, what is, you guys know what E is, right? E to the x. 1 plus x. You guys didn't want to learn about this, but I guess I should do one. You guys know this. Better know that. Like if you leave college not knowing that, we get hate mail at this part. Don't know this much at least. You gotta know that. This is like very important. A Taylor series for E to the x, if you put in I theta in here, you get like I theta, right? Blah blah blah. You'll see that you get a fact, you get an I factor, and you get a real factor, and you get a complex factor. This will divide up into a cosine and a sine. So this, if I look at e to the I theta, this will look like cosine of theta plus I times sine of theta. Right? If I multiply that by r, get r cosine of theta plus I times r sine theta. You guys seen this before? If I do this r cosine theta. It's like polar coordinates. So what I'm saying is you can represent complex numbers in polar coordinates this way, analytically. And then when you multiply, there's beautiful homomorphism. R e to the I theta times some other guy, S e to the I psi. Well, all your exponential rules apply from just basic analysis of this sequence. Everything applies, and commutativity. So you get your exponentials, you get RS. That's e to the I theta plus psi. Which is what Gail and John were getting at. If I have some other guy out here, S with angle psi, multiplied by Z, I'm going to add my angles. I'll rotate this by an extra theta. And I will sort of scale the norm by R. I'll scale the length by R. That's length. That's angle. That's what multiplication does. Why am I talking about this? Tell you why. I wanted to prove the fundamental theorem of algebra. Let's make this a monotheorem. It's no harm. If you look at a polynomial, and you take an n power, if you look at polynomial, you look at z, it's z to the n plus other stuff. When you get big rate in norm, when you get, in other words, get really far from the origin, this polynomial looks a lot like just z to the n, because the other terms are much lower order. So you like, a billion to the 10th power is a lot bigger than a billion times. So like, and when you get bigger, it gets even more. So and that's I want to finish this argument, but I'm not going to have time. Okay, I'll do it next. I'll do it on Monday. I'll finish this argument. Let you digest just a little bit. But yeah, we're going to slow down, and I'm going to restructure the last few weeks. All right.
I knew there was something missing about
What's that?
But I knew there was something missing about carbon.
I totally forgot about that. Like now that it's
Something
happening
really
again, I
bad.
remember last week, refreshed me. I like how you